We're going to start today's lecture reviewing theorem of iterated expectation that we talked about at the end of last time. So the theorem, as written out, was that if we have two random variables, x and y, then if I look at the expected value of x, this is the same thing as taking the expected value of x given y. And so this is called the iterated expectation. Spell that right. And the reason is because we iterate, or we do multiple expectations. So instead of calculating expected value of x directly, if I know something about the distribution of x given y and about the distribution of y, I can calculate the expected value of x with this theorem. So we need to review a little bit about what this notation means. So recall that we've looked at, up to this point, we've looked at, say, the expected value of a random variable x given another random variable y is equal to some value little y. And so here, this little y is just some number, and x and y are our random variables. And we had a definition for this. It was the integral of x times the conditional Pmf of x given that value little y, and we integrate with respect to x. And so it looks a lot like the expected value of x, except instead of f of x, we have now f of x given y. And when we calculate this integral, this just gives us some number, some real value. And so we can consider a function that takes in a real number and spits out a real number, defined as, for each value little y, this is y is some real number, g of y is going to be the expected value of x given y is little y, right? And this is a valid way of defining a function because for each value, little y, that we input into the function, we get another number, expected value of x given y, and that's just another number. So this is a very particular function. And we can then, because we have some function, so here, as I wrote up here, g is just a real valued function. We are allowed to look at, so we can consider, say, g of y, where y is my random variable and g is a particular real valued function. And we've looked at how to deal with functions of random variables, and so we know something about how to deal with a function of y. And now we're just picking a particular function that is defined by the expected value of x given y. And so you could imagine that you could kind of plug it in the formula. You could say this is expected of x given y is equal to, now instead of little y here, we could plug in big Y. Although the notation looks a bit silly. So what we tend to write, we tend to just write expected value of x given y. And at the end of the day, this thing here is just some notation. And what it stands for is it stands for g of y, where g is defined up here. So just as a recap, expected value of x given y is equal to some little y is a number. And expected value, this notation, expected value of x given y, close bracket, is a random variable. It's a particular random variable that we get by taking a transformation of y, and that transformation is the expected value of x given y. So in our theorem, we have the statement that expected value of x, which I think we're all familiar with at this point, is equal to the expected value of x given y. And we can make sense of this notation now because this thing here is a random variable that is a function of y. So it's some function of y, i.e. it's some g of y. It's a particular g of y, hence the notation, but it's some function of y, and so it's some random variable. And thus we can take its expectation, so we could ask for the expected value of g of y, and we can kind of, instead of using the g notation, we should just ask for the expected value of x given y, right? Because this thing in here is a random variable, and so we can ask for its expectation. And when we ask for its expectation, what we get, according to the theorem, is that we just get the expected value of y. So somehow we get rid of the y dependence. And you should note that this outer expectation is with respect to y. That is, when I calculate it, I'm integrating against the PDF of y, right? So if I were to write, if I look at the expected value of g of y, this would be the integral of g of y, f of y, dy. And so it's kind of with respect to y, that is, the PDF against which I integrate is f of y. And so sometimes people will write a little subscript y out here to remember, you're not going to multiply by the PDF of x, you're going to multiply by the PDF of y. So let's do a real quick proof of this theorem. And the proof of this theorem just uses some definitions. And so we're just going to prove this in the continuous case, although the discrete case is very similar. So in the continuous case, expected value of x is, of course, the integral of x times f of x dx. And we can use a fact, which is that the PDF of x, that is the marginal distribution of x, can be written as, we know we can get that by marginalizing out y from the joint. So we could write this as integrating over y, or integrating with respect to y, of the joint f of x, y. And so one could replace that in our formula. This would be x times the integral of f of x, y, dy, and of course we still have our dx out here. Okay, so what other tricks do we know? Here's another fact. We have this fact that is basically some version of Bayes' formula, or we have a definition, alternatively, of a conditional PMF or PDF, and that would say that f of x given y is the joint over the marginal. So f of x given y is f of xy over f of y. And we could alternatively rearrange this and say, so equivalently, f of xy is f of x given y by f of y. And now we can just plug this in our formula here. Integral x, integral with respect to y, and now we're replacing f of xy with f of x given y, f of y, and then we're just going to rearrange things. So what I'm going to do is I'm going to interchange my integration order. So first of all, I can pull these integrals all the way to the left. This is x, f of x given y, f of y, and now I'm just going to say dx dy. And what else can I do? I notice that this, if I Well, first of all, I can pull out my inner integral depends on x only. So I can actually factor out this f of y. So let me factor that out first, and then we're going to recognize what this inner integral is. X given y, f of y. Whoops, that can come out, right? So we can just pull that out. So that's the inner integral. And then we're left with an f of y and a dy. And well, what I'm going to recognize here is that this is exactly the formula for the expected value of x given y is some value little y. So for whatever value little y I choose, that is expected value of x given y is little y. And so if I were to call this thing, as I did above, g of y, this would be the integral. The whole inner integral I'm calling g of y, f of y, dy. And this is the expected value of g of y. But of course, g of y in our case here is g of y is expected value of x given y, as we discussed above. So I could write this how it more typically is writing as expected value of x given y. And I'm going to put a little subscript y here to remember this outer integral depends on y, right? There's an f of y here. This outer integral depends on y. So that's the theorem. So one more time, the theorem, which we're going to write and then we're going to do some examples, is if I want the expected value of x, but I don't know the marginal distribution of x, if I know something about y and I know something about x given y, I can calculate expected value of x given my iterated expectation formula. Iterated expectation. We saw last time at the end of lecture some examples how to do this, and this is going to give us a real quick shortcut on how to solve these problems. So let's look at some example that we saw last time, which is x given some value of y has a binomial distribution n, where the number of trials is y and the probability of success is p, and y marginally has a Poisson distribution with some unknown parameter lambda. So we did this problem last time. We actually calculated the expected value of x. But now I have a shortcut, which is the expected value of x I can calculate with my iterated expectation formula. It is expected value of expected value x given y, close brackets. And so I basically need to figure out the different parts of this to do the calculation. First thing I'll need is, first I want to look at expected value of x given y is some value little y. Now, conditional on knowing the value of y, x is binomial yp. And so the expected value of a binomial yp is y times p. So this is our g of y. P is just a constant, right? So if I look at the expected value of x given y, this is g of y, which you could write, say, as y times p. It's a reasonable way to write that. So it's just a rescaling in this case. The conditional expectation of x given y is just a rescaling of y. What I want, expected value of x, this, of course, expected value with respect to y of yp. All right, now this dependence here outside on y seems a bit silly because we see obviously this expected value just depends on y. And what are my rules of expectation? Constants can come out. So it's p times the expected value of y. Y is a Poisson. What's the expected value of Poisson? Lambda. So it's p lambda. And this is what we got last time. Lambda p or p lambda. Much quicker than how we solved it last time. Okay, let's continue on. Let's do another real quick example. I'll show you how nice this theorem is. Example, x given some other random variable p is a value little p. We're going to say is a binomial np. So now p is kind of random. Marginally, we're going to say p has a beta, let's spell that, distribution with some parameters alpha and beta. So x is, instead of now being the number of samples in our binomial experiment being random, now we have the probability of success being random, right? If you recall, beta distribution is distributed between 0 and 1, and depending on these parameters, alpha and beta, has some shape there. So it's a reasonable type of random variable for the probability of success. It's bounded between 0 and 1, which is what has to be true of probabilities. So very similar to the last one, and generally this might look pretty daunting as long as we remember some facts, or we can look up some facts about the beta distribution. It's very similar to the last one. First, let's look at the expected value of x given p is some value little p. If x given p is little p is binomial np, then this expectation is just np. And so the expected value of x given p, the random variable, is n times p. So I'm using capital P now as the random variable, or you could write this as g of lowercase p. And our third step is the expected value of x we can get by taking the expected value of the second step, x given p. So this is the expected value of n by p, and as a constant comes out, n by the expected value of p, and you have to remember you have to look up what the expected value of a beta random variable is. It's alpha by alpha over beta. So in this case, expected value of x is just n times the expected value of p. That seems like a nice little result. So there's this theorem for iterated expectation, and of course variance is just some certain kind of expectation. So we can also get a theorem of kind of iterated variance. It's actually called the Law of Total Variance. And it's a little more complicated than the iterated expectation, but it's proved using that theorem. So the proof of it is actually pretty simple. The statement is that the variance of a random variable x, and here's how we're going to remember it, the variance of x is the expected value of the variance, x given p, plus the variance of the expected value of x given p. And I'll just say proof is similar to the other theorem. It's just going to be a little longer because we have two parts. So here, again, the expected value of x given p is a random variable. And we can similarly define the variance of x given p as a kind of similar random variable, the same way we define the expected value of x given p. And so one is an expectation, the other is a variance. And the theorem gives us a way of calculating the variance of x. It's the expected value of the variance plus the variance of the expected value. That's how you want to remember that one. So if we go back to our example here, x given p is little p, has a binomial np distribution, and p marginally has a beta distribution. We could ask for the variance of x. In this case, we found this expectation. What's the variance? So it's going to be a little bit more involved than the other examples, but not too bad. First, we saw last time that the expected value of x given p is little p is np, and the variance in this case of x given p is little p is just going to be, well, the variance of a binomial np is np by 1 minus p. So we can think of the expected value of x given p as n by p, capital P now, it's a random variable, and the variance, kind of correspondingly, of x given p is np by 1 minus p. Capital P, again, is our random variable. And we have two parts to our theorem. We want to calculate the variance of the first one here and the expected value of the second one. So variance of expected value, x given p, is the variance of np, bring out the n as an n squared, variance of p, and you got to remember that the variance of a beta random variable, not that I expect you to memorize this, is alpha plus beta squared, alpha plus beta plus 1. So that's the first part of our theorem. The second part of the calculation is we need the expected value of the variance of x given p, which is the expected value of np by 1 minus p, which I can write like this. I can bring out the n. It's n expected value of p minus p squared. I can, of course, distribute expected value over this minus sign, so it's n expected value of p minus n expected value p squared. And you have to look up the moments for a beta random variable. We know the expected value. You'd have to figure out the second moment, which of course you could calculate given the variance. In this case, I'll save you the algebra to figure this out. It's n alpha beta over alpha plus beta plus 1. So those are our two components, and to get the variance of x, we just add these two together. So I'm just going to say add to get variance of x, which is what we wanted. All right, if we go back up, the question was, what's the variance of x? So it's a bit more involved, but it's very similar. Okay. We're going to switch gears here. So we've talked kind of extensively about conditional distributions, and we're going to talk today about a particular bivariate distribution that's very important, and that is the bivariate normal distribution. So in the univariate case, we had a normal, say, mu sigma squared distribution, and the PDF looks something like this, centered at mu, and the broadness of it was related to the variance sigma squared. It had that kind of characteristic bell shape. In the bivariate case, we have what's called a bivariate normal. And so now we gotta look at this thing in 3 space. So I can have an x, a y, and then I'm going to have f of x comma y. So in this case, it was just x by f of x. And in this case, we kind of get like a 3-dimensional bell. So you can imagine it looks something like this. It's not a great drawing. Let's try that one again. Something like this. And it's kind of 3-dimensional. So if you take slices of this thing, it's kind of a bell. So I'm tempting to draw here. that. One useful way to think about it is if we look at the contours of this thing. So we've got to look down on the xy axis. Its contours are going to be ellipses. So if we look at our kind of down on this thing from the xy axis, it's going to be, of course, the center of this thing is now going to be a point called mu x, mu y. And the shape of it is going to be, so this is what's called the mean. And the shape is going to be determined by the variance of x, the variance of y, and rho, which is going to be the correlation between them. If we look at this thing down from the from kind of above, what we get is the center is the point mu x, mu y, and then we have ellipsoidal contours that look kind of like this. It's supposed to be all nested within each other. And the kind of skewness slash eccentricity of these contours is related to the correlation. So, in particular, if x and y, my two components, are uncorrelated, I'm going to get circular contours that look like this. And alternatively, if x and y are highly correlated, if I look at my contours, I'm going to get very elongated ellipses that will look a lot like this. It's going to tell me they're very highly correlated. So that's kind of the intuition behind the bivariate normal. Let's look at it in more details. So the bivariate normal has a bunch of parameters. It has the means, so it's parameterized by the means, mu x and mu y. So often we'll combine these into one parameter, mu, which is a two-component vector, mu x comma mu y. And it has the variance slash correlation information. How are x and y related to each other? So that is sigma squared x, sigma squared y, and rho, which is a correlation between them. You can encode all of this in a matrix. We're going to say capital sigma, where capital sigma is the following matrix. On the diagonals is sigma x and sigma y squared. And on the off diagonals, it is sigma x, sigma y, rho. Sigma x, sigma y, rho. Those off diagonals are the covariance. So if I have a variance of y being sigma squared y, and my variance of x is sigma squared x, and my correlation is rho between x and y, then my covariance would be sigma x, sigma y, rho. So these are the covariances. And this whole matrix itself is called the covariance matrix. And it encodes kind of variability in the data set. Not only how variable is x, how variable is y, but how are x and y related to each other? What is their covariance with each other? It's a symmetric matrix because the two off-diagonal entries are equivalent to each other, and on the main diagonal, it has the variances of these two things. So it has, what is that, 5 parameters. Mu x, mu y, sigma squared x, sigma squared y. Given these parameters, we can look at the PDF. So what is the joint PDF? So here we have my bivariate random variable, x and y, has a bivariate normal. Maybe I'll write it like that. And I could specify all the parameters if I want. Mu x, mu y, rho, sigma x squared, sigma y squared. The joint PDF, fxy, takes the following form. This is a long expression. 1 over 2 pi sigma x, sigma y, square root 1 minus rho squared, exponential, and in my exponential argument is all of the following. 1 over negative 1/2 times 1 over 1 minus rho squared, and then all of that negative 1/2 times 1 over 1 minus rho squared is multiplied by x minus mu x over sigma x quantity squared plus y minus mu y over sigma y quantity squared minus 2 rho x minus mu x over sigma x. I'm going to run out of room here. So let's just bring this all down to a new line. Y minus mu y over sigma y. Close, close. So that's the PDF. You can see it looks a bit like the normal, the univariate normal. It has a 2 pi, has the variances in similar-ish places. This is one way of writing it. This is the way it would be presented if you don't know anything about linear algebra. But since that's a required course for this one, we have a much simpler way of writing it, and it will generalize better when we talk about the multivariate normal in a couple lectures. In that case, the simpler way to write it is given, so mu is my mean vector, and capital sigma is my covariance matrix. In this case, the way we can write this thing is 1 over 2 pi one over square root determinant of sigma exponential negative 1/2 and if let's call z x comma y, I can write this then very simply as z transpose, so prime for transpose, sigma inverse, inverse matrix, z, close parens. So this is the real adult way of writing the bivariate normal. You parameterize in terms of mean vector and a covariance matrix, and in that case it's 1 over 2 pi, 1 over square root of the determinant of the covariance matrix times the exponential of negative 1/2 z transpose sigma inverse z, where sigma inverse is the inverse matrix of sigma, and z is just my shorthand for x comma y. It's a two-dimensional vector. So I'll let you think about that and why it's equivalent to the previous one, but that's a good thing to know. Okay. So practically, what are some nice, useful facts of the bivariate normal? Useful facts to know. 1, x marginally as a normal distribution with mean mu x and variance sigma squared x, not surprisingly. And there's a corresponding fact for y. So marginally, they're just normal with their respective means and variances. The correlation between x and y is, of course, rho, as we claimed. So I'm going to write these facts. I'm not going to go through and prove them today, but you have the tools now to prove them. So marginally, they're normal. The correlation is rho. Let's hope that's how we parameterized it. Third fact, if I look at ax plus by, it's a linear combination of two normals. We know how to add normals if they're independent, but they may not be independent in this case. They may be correlated. In this case, we get a super simple formula. This is also normal with mean a times mu x plus b times mu y, and variance a squared sigma x squared plus b squared sigma y squared plus 2ab sigma x sigma y times rho. So if I want to look at a linear combination of two normals, which are I have a bivariate distribution and with a correlation rho, I get a nice formula. It's still normal. It has a bit more complicated variance, but it's still normal. This is a supersedes the first point if I were to choose a is 0 or b is 0 and the other one to be 1. So if I said a is 1, b is 0, I would get just x, and it would reduce to this first case. And alternatively, if I say b is 1 and x and a is 0, I would get the margin of y. Okay. This is actually a characterization of the bivariate normal. So this is characterization of bivariate normal is the converse of the above theorem. What I mean by this is that it's an alternative way to define the bivariate normal. Is we could say x and y has some bivariate normal distribution if and only if ax plus by has some normal distribution with whatever parameters for all possible values of a and b. So one way to define the bivariate normal is give me the PDF, as I did above. The other would be to say, if every linear combination of the two random variables is normal, that is the same thing as saying they're bivariate normal. So if they're bivariate normal, any linear combination is normal. We saw that in the third fact. But conversely, if I can take any linear combination and that gives me a normal, they must be jointly bivariate normal. That's not particularly useful in this case, but can be sometimes useful to just remember that bivariate normals are kind of the set of characterized by the set of all linear combinations being normal. Okay. The fifth fact I want to write here is the exception to the rule. So recall when we talked about independence, we had a theorem that said if x is independent of y, then we could show, and we did show, that the correlation between these two things was 0. Independence implies 0 correlation, or equivalently 0 covariance. So this was an implication one way. I said if x is independent of y, then they're uncorrelated. But they said that generally does not go the other way, and they gave a counterexample. This, that is bivariate normality, is the one case It is another characterization of the bivariate normal that goes the other way. So here's the theorem. It's a converse in only the case of the bivariate normal. The theorem says, let's move this up here, if xy has some bivariate normal and so they're jointly bivariate normal and they are uncorrelated, then they are independent. So another shorter way for saying, a way of saying this for bivariate normal independence equals uncorrelatedness. But that is only true for the bivariate normal. It will not be true for any other. That's a very useful fact and shows up all over the place in statistics that actually if we assume things are bivariate normal, if we want to show they're independent, we just need to show they're uncorrelated. And it's very useful. Let's do a proof of this. It's actually not so bad. And it's a good kind of review of independence. So let's write out our joint PDF. This thing's a bit cumbersome. What was our joint PDF for bivariate normal? 1 over 2 pi sigma x sigma y root 1 minus rho squared. And we had all of that multiplied by some exponential, negative 1/2, 1 over 1 minus rho squared. And then we had this thing that was x minus mu x over sigma x squared plus y minus mu y over sigma y squared plus 2 rho x minus mu x over sigma x times y minus mu y over sigma y. And I had to close all my brackets, right? Okay. So this is the general case. Our theorem says what we're assuming is that the correlation between x and y is 0. And if we believe one of the facts above, rho in our parameterization is the correlation. So rho is 0. That's going to help a lot. This thing turns into a 1. This thing turns into a 1. This thing goes to 0. So what we're left with here, 2 pi sigma x sigma y, 1 over that, exponential, negative 1/2. And I'm going to break up this exponential. It's x minus mu x over sigma x squared times exponential 1/2 y minus mu y over sigma y quantity squared. That's all that I have. If rho, my correlation between these two things, is 0. If I call this first function, which is just a function of x, h of x, and I call the second one, which is just a function of y, g of y, what I've shown is that my joint PDF can be factored as h of x times some g of y. So, by my theorem that we said last time, x and y are independent. If I can factor either the joint PDF or the joint CDF, then I know things are independent. So that shows it, that for bivariate normal, independence is the same thing as uncorrelatedness. Okay. So that's a quick review of the bivariate normal. What we're going to do for the rest of today is we're going to look at bivariate transformations. So since everyone's favorite topic was univariate transformations, we're going to look at what if I transform a 2-component random variable. And this is really getting to some powerful mathematics that will allow us to prove a lot of nice results. So in the univariate case, right, we looked at, say, if g was a real valued function, we looked at what does g of x look like? And for the bivariate case, what if we take a function r2 to r2 and look at g of x comma y? What can we say about that? So that's what we're going to talk about today. And we're going to derive some theorems as we go through this that will look very similar and generalize all the stuff we said in the univariate case. So for notation with bivariate transformations, the kind of typical way to do this is, so I go from a pair of random variables x comma y, I have a two-dimensional function g, and I'm going to spit out two new ones, and I'm going to call them u and v, just for fun. Those are my new random variables. So examples of this is I could say u comma v could be some transformation of x and y. Maybe it's x squared y log of y. So it's two components, right? 1, 2. Or I could say u comma v is negative x over y x times y. And you can think of as many possibilities as you have time, right? So we're going from originally two variables x, y to two new variables u comma v. There's going to be a lot to keep track of here. Let's look at the discrete case. So discrete. Okay. So what's going on in the discrete case? So x and y are discrete. And what I'm going to do is I'm going to define a set A sub u v. And A sub u v is going to be the set of all pairs x and y such that when I map them under my transformation, I get u comma v. So if my transformation is u v is g1 of xy, comma g2 of xy, so that is u is g1 of xy, v is some other g2 of xy. So let's just go back. In our example above here, this is like g1 of x, y, and this would be g2 of x comma y. There's just the two components of the function. So it's a function, right? Remember that g is a function r2 to r2. Not only takes in x and y, but it spits out u and v. Okay, so given that, so our two components are g1 and g2. So a sub uv is all pairs x and y that map onto this to u and v, right? It's basically going to be the inverse image. So it's all pairs x and y. When I plug in x, y, I get u under the first component, g1. And if I plug it into my second component function, g2, I get v. So it's basically the inverse image of x comma y under g. Right. So the picture here, we have two spaces, both are 2. And if I have a point over in my transform space, which is supposed to be u comma v, right? And I have a function g which maps xy over here to my u comma v here. So if I have some point uv, if I look at all points over here that map under g to uv. So this is my a sub uv, which you could write as g inverse of uv. Let's say it like that. Let's get a notation. Let's write it like that. Sure. G inverse of UV. It's the inverse image. So what does that do for me? This is basically, if you go back to our univariate case with discrete random variables, we're basically just generalizing the result there. So I want the PMF, that is the joint PMF of u, v. And I want to get that from the joint PMF of x, y. So joint PMF of uv, I'm going to say f uv of uv. Lots of notation. So the subscript here reminds us this is the PMF of u and v. It has two arguments, little u and little v. This, in the discrete case, is just the probability that capital U is little u and capital V is little v. And this is equivalent to saying if capital U is little u and capital V is little v, this is the same thing as saying that x and y are in the inverse image of little u and little v under G. So same thing as being in the set A, right? Let's go back up to our picture. If we're at this point uv over here in our uv space, so that's the same thing as xy being in that set A sub uv. So that's an equivalent way of writing that. And this, we know we can calculate this by summing over all pairs x and y in this inverse image. And we can sum the probability that x, little x, and y is little y over all pairs x and y in A sub uv, which, of course, we know that this thing, x is x and y is y, is just what we call the joint PMF of x comma y. So I'll write it like that. F of f subscript capital X capital Y of my arguments little x little y. So fortunate thing about probability is there's a lot of kind of bookkeeping notation. So this is a bit of an abstract theorem, but basically it just says if I want to get the joint PMF, I just sum joint PMF of u and v, I sum the joint PMF of x and y over the appropriate range. So let's look at an example of this. So example. So this is, we're going to develop kind of a useful little theorem here. So here's my example. X and y are going to be two random variables, and I'm going to say they're independent of each other. So x independent of y, and marginally, x is going to have a Poisson distribution with parameter theta, and y is also going to have a Poisson distribution with a different parameter lambda. Right, so these are discrete. We know the marginal of x, we know the marginal of y, and we know how they're related. They're independent. So we have enough to specify the joint PMF of x and y. So in this case, joint PMF of x and y is just the PMF of x times the PMF of y. Why is that true? They're independent. So we can just multiply like that. And we have to remember what the PMF for a Poisson is. X is Poisson theta, so its PMF is theta to the x, e to the negative theta, over x factorial. And y is Poisson lambda, so its PMF is lambda to the y, e to the negative lambda, over y factorial. Okay. Now let's get to the transformation. Let u be the sum, x plus y, and v be y. So this is my transformation. You could write this as u comma v is x plus y comma y, in which case my first component function, g1 of xy, is just x plus y, and my second component function, g2 of x comma y, is just y. Okay. So obviously what I'm going to want is I'm going to want the joint PMF of u comma v. So first, what we want to do, we need to determine this set A sub u v, which is the set of all x and y that map to a u and v. So to get this, let's notice that u is x plus y and v is y. So if I look at u minus v, I get x. And of course, if I want to get y, I just look at v. So if I know x and y, obviously I can plug in my formula and get u and v, sum x and y, and just take y. But if I know u and d, I can directly get x and y back. If I know u and d, well, y would be v, and x would be u minus v. So what this is saying is that g is invertible. For each value x and y, we get one u and v. It's a function. For each u and v, we get exactly one x and y. It's invertible. So, so that's a really nice fact, because what this says is that A sub uv, which you could say is like inverse image of uv, is just the pair u minus v and v. Oops, that's not a u, that's a v. So A to uv is just one, and you could write it as a set if you want. It's just one pair. And that shows up in our formula, right? Because if I want the joint PMF of u and v, this was a sum over pairs x and y in A sub uv of the joint PMF of x and y. But in this case, that really simplifies, because in this case, this is just, well, we can just write it as f, the joint xy, the joint xy. Well, what pairs xy are in A sub uv? Well, it's just going to be u minus v, v. And now we just have to plug in above what our joint was, right? So if you go back and look at what the joint was, when you plug in for x, u minus v, and for y, v, you get theta, now not to the x, but to the u minus v. E and the negative theta stays the same, and instead of having 1 over x factorial, it's 1 over u minus v factorial. And then we get a lambda, not to the y now, it's lambda to the v, e to the negative lambda, and we get a, instead of 1 over y factorial, it's 1 over v factorial. So this is the joint of u and v. Now, a good question is, why do we care about the joint of u and v? Why do we care about this transformation? Well, we may or may not. A very useful thing about this example is, if you recall, u, x plus y, and v was just y. If I want to get the distribution of x plus y, all I have to do is get the marginal distribution of u. So the question is, what is the marginal of u? If I get the marginal of u, then I basically have derived what the sum of two Poisson random variables is. So the marginal of u, of course, f of u, let's write it like that, f u of u is, what do? We marginalize out v. So we take the joint and we sum over the possible values of v. In this case, what are our possible values of v, right? V is y and u is x plus y. So v can never be bigger than u. It could be 0. Y is a Poisson, right? So this thing is Poisson. So it could be 0. Poisson's allowed to be 0. But it can never be bigger than u. So our sum only goes up to u. So if we continue this as the sum, v0 to u, and then we basically take this whole thing and we plug it in here, right, from above. Now it's a bit nasty of a sum, so what we want to do is, first what we want to do is note that we have, so this is just an aside here to simplify things, we have a 1 over u minus v and 1 over u minus v factorial times a 1 over v factorial. This is equivalent to 1 over u factorial u choose v. Right, if I just use move my u factorial to the other side, that's exactly u choose v. And so let's continue this sum down here. This is a sum, and we're going to pull out everything out of that sum. So everything out of this thing here that does not depend on my index, v. So there's a bunch of stuff that doesn't depend on v. What doesn't depend on v? Anything involving u. So I'm going to get an e to the negative, and I can combine as theta plus lambda. I can combine those two because I have an e to the negative theta and e to the negative lambda. I have, if I replace 1 over u factorial times 1 over v factorial with this thing, there's a u factorial that comes out. That does not depend on v. And then everything else I think depends on v. So what I'm left with is my sum goes 0 to u. I have a u choose v after using this thing to replace part. And what am I left with? I'm left with a theta to the u minus v and a lambda to the v. So our friendly binomial theorem says that this thing is equal to lambda plus theta to the u. And so what I'm left over with, I can replace that with lambda theta to the u, is e to the negative theta plus lambda plus lambda to the u over u factorial. And now, what we do is we recognize that this is a Poisson theta plus lambda. That is u, which is, remember how we defined u, is x plus y distributed Poisson theta plus lambda. So this motivates a theorem. What's the theorem? Theorem, what we just proved, and it's a nice example of our first Bivariate transformation, is that if x is independent of y, x has a Poisson marginally with theta, y marginally Poisson with lambda, then x plus y marginally is a Poisson also, but I just add the parameters. Poisson theta plus lambda. So that's a very nice result. Most distributions, if I just add them, if I add random variables with this distribution, it doesn't stay in the same family. It doesn't have to be Poisson. Much less is it easy to just add the parameters. So we've seen this as normal. We've seen this now with Poisson. I'm going to show you kind of the cases where it works nicely, and most other cases it doesn't work nicely. Okay. So that's the discrete, an example in the discrete case. And discrete doesn't have too many real tricks. You kind of just have to brute force your way through it. And now let's look at the continuous case. All right, continuous case. So in this case, we're going to derive a theorem very much like the univariate transformation theorem, but for the bivariate case. So u comma v is some function g of x comma y, so that u is g1 of x comma y, v g2 of x comma y, and we're gonna, so first of all, we need to assume that x and y are continuous random variables. And what do we need to assume about g? Well, in the univariate case, and same in the bivariate case, we need to assume that g is invertible and that g is continuous and differentiable. So we're going to say continuously differentiable. And that is in now both coordinates. Right? Because g now is a function of two variables that gives us two variable output. So function R2 to R2. All right. What's the theorem? In this case, if I want now the joint PDF, because we have continuous, of uv at values little u and little v, I can get this from the joint PDF of x and y. I'm going to plug in the inverse function of g. So that is the inverse function is a function R2 to R2. And I'm going to multiply by the absolute value of the determinant of what I'm going to call derivative of g inverse with respect to u, v. Okay, so that's the theorem. I'm going to put a box around this result. We're going to talk about the various parts of it. Notice that, right, so g is a function R2 to R2, and so g inverse is a function also R2 to R2. And I can call the components g inverse of uv is going to have two components, g1 inverse of uv and g2 inverse of uv. Now, you have to be careful with this notation because it's not necessarily true that g1, that the two component inverses are just the inverse of the components of the other function. You got to actually derive the bivariate inverse. So when I plug this in, I just write g inverse. This is a number in R2, right? And of course, the joint PDF takes two-dimensional vector, right? So that's an okay thing to do. That I think is pretty straightforward. We have to explain this other part. Now, this should look somewhat familiar because in our univariate case, we said that f of, what did we call it? We called it y in that case. Or we can say f of g of x at some value little y was I take fx, I plug in g inverse of y. Well, that looks familiar. That looks similar. And I said times the absolute value. If I looked at the derivative of g inverse with respect to y. And now we have the absolute value of the determinant of this derivative. And this thing here is what's called the Jacobian. So that's my notation for it. Sometimes people just use j. I like to remember it's derivative of this inverse. So let's look at this Jacobian a little more in depth. So g inverse of uv, I'm going to say has two components, functions, g1 inverse and g2 inverse. So just keep that in mind. The general rule let's say generally, if I have a function h that goes R2 to R2, so you could say h of xy is h1 of xy, comma h2 of xy. The Jacobian of h is, and you could write it how I wrote it, dh with respect to both x and y, is the following matrix. It is dh1 dx, dh1 dy across the first row, dh2 dx, dh2 dy across the second row. And you can imagine you could generalize this to kind of the multivariate case. So the derivative of the first function in the first row, derivative with respect to all the variables, second function in the second row, derivative of all variables, etc. So if I have this function g inverse R2 to R2, where g inverse of uv, let's say has two components, g1 inverse and g2 inverse of uv, then my Jacobian, dg inverse, derivative with respect to u and v, is the following matrix: dg1 inverse du, dg1 inverse dv, dg2 inverse du, dg2 inverse dv. So that's the Jacobian. And then you just have to remember for determinants, right? So there's a determinant in this formula that for a 2x2, 2x2 matrix, if you remember back to linear algebra, determinant of A, if A is the matrix A, B, C, D, determinant of this thing is first diagonal minus second diagonal, AD minus CB. So that's the theorem. Let's just write it out one more time. If we have u and v is some two-dimensional function of x and y, then if I want the joint PDF of u and v at little u, little v, I take the joint PDF of xy, evaluate it at, I could say g1 inverse uv, g2 inverse uv times absolute value, determinant, derivative of g inverse, or the Jacobian of g inverse with respect to u and v. Closed form. So what I'll do is, in order to calculate this, is so what I do is I get my function g. I find g inverse. I'm gonna then find Jacobian and take its determinant, and then I can plug in above for the values. Okay, so let us look at one example of this. Let's just do a setup of what one might look like. So here's going to be the setup. uv is x plus y, comma, x minus y. So in this case, u is g1 of xy is x plus y, and v, g2 of x comma y is x minus y. So step 1 is let's get g1 inverse and g2 inverse. This is the inverse components of the component function of my inverse function. So notice that if I take u plus v and divide by 2, I'm going to get x. And if I look at u minus v over 2, that will give me y. So basically I've solved for x and y in terms of u and v. So g1 inverse of uv, that is the value that gives me x, is just u plus v for 2. And g2 inverse, the function that gives me y from u and v, give it u and v, gives me y. To do that, I just have to look at u minus v over 2. And so that's part. What I now need is my Jacobian, or what's often called Jacobian determinant, because it's the determinant of the Jacobian. And we can calculate that thing. So I denote it as g inverse derivative with respect to u and v. And to recall, it's g1 inverse du, dg1 inverse dv, dg2 inverse du, dg2 inverse dv. In this case, our functions are real simple, right? So g1 inverse is u plus v over 2. So if I take the derivative with respect to u, I get 1/2. If I take the derivative with respect to v, I get 1/2. g2 inverse is u minus v. Derivative with respect to u, 1/2. Derivative with respect to v, negative 1/2. And so if this thing is j, then determinant of j is 1/2, negative 1/2 minus 1/2, that's 1/2, which is negative 1/2. All right, it's negative 1/4 minus 1/4. Absolute value of determinant, which we'll use in our formula, is just 1/2. Okay. So from this, if I want to get, so 3 is kind of plug in. Well, let me write that down. So 3 plug in. If I want f, joint PDF of uv, add some values to little e, little v, what do I plug in? Joint x comma y, g1 inverse uv, g2 inverse uv, and absolute value determinant of Jacobian. Now we basically determined all these parts. We haven't actually specified ever what x and y are distributed as, so we can't really totally solve this at this point. But it will be something. g1 inverse of uv is u plus v over 2. g2 inverse of uv is u minus v over 2. And this thing, absolute value determinant of Jacobian, just gives us 1/2. Okay. Let's stop for there for today.